This meeting is being recorded.
Okay, good afternoon, everybody. About a small number of you have completed your midterms at this point. Most of you still will be doing that with me on Thursday and Friday. Good luck to those of you who are still preparing. Good luck with your studying. Two quick announcements for us today. We will be having a quiz next week. There's quiz will be on the definitions from chapter 1 of our book. They're up here, 2 handouts in physical form if you would like them. One of those handouts is a copy of what that quiz will look like. It's just got a whole bunch of blank spots for you to type, or not type, but write out the definitions. And you'll have to know the definitions for that. Again, all the definitions, things that we have or will have covered in class by that point. And but if you want a gold standard cheat sheet of the quiz, I have also included that in the repository for this week. The quiz.pdf is the handout up here, and the quizkey.pdf is just the answer key with those definitions. Again, one of the hard parts about this class, one of the ways that students commonly don't do as well as they would like in this class is because there are so many things, so many mathematical terms and equations going on here. And we'll be talking all about all of these things at a high level over the next couple weeks here. And if you don't have these things just memorized, then you won't be able to follow along with what we're doing when we're working on the different problems and covering different concepts. So you really have to, in this class, but in upper level math classes in general, spend some time just memorizing some of the key concepts. The strategy for memorizing these key concepts, like don't try to, there's a lot of weird symbols and everything in these equations. Don't try to just like memorize the picture. Try to memorize the intuition, understand the intuition, and that will make writing the definitions easier for you. So it should be some combination in your preparation of making sure you understand the intuition behind all these terms and making sure that you understand the notation. Like the last quiz on the definitions, you don't have to write exactly, like symbol for symbol, exactly how I have things here. As long as you have something that's mathematically equivalent, then you will be good. Okay, so that's first announcement here. That's again a week from today, next Wednesday, that's quiz. This weekend, your PageRank programming assignment is due this Sunday at midnight. We already had the one extension from last Sunday. There won't be a further extension, so there will be the late penalties applied if you don't get it in by this Sunday. I'll have the office hours again this coming Friday, so if you do have questions about the homework assignment PageRank, general, I'm available after class here. Handful of people every class session follow me up to my office when we spend 20 minutes or so talking about stuff. You're welcome to do that. Talk about the PageRank assignment now today, or office hours on Friday if you have any questions about that. Today in class, we're going to continue finish up talking about that first notes packet from the new textbook here that we're started talking about last week, and then we will maybe finish the second notes packet as well. Before we do that, before we get started technical stuff, any questions about anything administrative going on in the class? Everyone's good? Everyone's on board? Everyone's totally done with the homework assignment? You just haven't submitted it yet? I'm sure that's how things go. No, if I were a student, I was a student, believe it or not, at one point. I also waited till Sunday at, 10 p.m. to start, and then submitted it late. So I know how things go. But okay, so today, well, maybe one last review-ish thing. Last time, what we've been talking about so far has been computational aspects of machine learning. We started talking about that with PageRank in our first, month-ish of class. And then last week, we started with this new textbook, and this picture right here was one of the big things that we were talking about. illustrating a lot of these different terms. And then last class period in particular, we were talking about these different diagrams about visualizing the perceptron and how this diagram relates to the actual equation for the perceptron. I want to start today in class by doing an example problem related to this, related to what we were doing last time. This is on the first notes packet 1 for chapter 1, and problem 5, the very near the end of the notes packet. There are 3 parts to this. We'll do one of these problems in class. For two more zoom-ins, one more zoom-in. For these problems here, or in this notes packet, this is the type of problem that is the most important. So most important type of problem. Most important type of problem. Why is that the case? Well, one of the reasons why that's the case is this is exactly the type of reasoning that you will have to do when you go on to take, say, the data science capstone, or go out into the real world and do real world reasoning on problems that you haven't seen before, not from an academic context. And so let's talk about this problem and see how to do some of that reasoning based on what we've covered last lectures. And then we won't do all of this problem, we'll do one part of this, hopefully giving you the idea of how to complete the other parts of this. So this problem says that Alice has proposed shrinking the data points by a factor of alpha so that R will be smaller. Again, R is this radius of the data set. So recall that if we have a data set in 2 dimensions, we can draw it something like this. And we have like plus points, say, and minus points like this. And the radius of that data point of this data set, can try like draw a circle. This circle, let's do it again. The circle should be centered around the origin. And so maybe those pluses are a little bit closer, the minuses maybe a little bit farther away. But whatever the distance to the farthest away data point is, that's what we call the radius of that data set. And the idea here is that if we shrink the radius by a factor of alpha, then our runtime might be able to be faster. Why might the runtime be faster? We'll recall from last time that, or 2 times ago now, that the runtime of the PLA, the runtime of the PLA, the perceptron learning algorithm, is O of R squared, this norm of W star squared divided by rho squared. This was the number of iterations here on the left-hand side. Anytime we have one of these iterative algorithms, which all of our algorithms in this class will be, we have to figure out how many iterations will happen and then multiply by the runtime per iteration. So the big, complicated, scary thing on the left-hand side was our bound on the number of iterations. And then the simple thing on the right-hand side here was the runtime per iteration. And the idea here is that if we are somehow, like we have an R in here, the radius of our data set is in the numerator of this runtime. And if we were to able to somehow make this radius of the data set get smaller, then maybe our runtime would be faster. And so Alice is proposing one possible way of doing this by taking our data set and every data point dividing it by alpha. And in particular, if we have this equation right here, then I'll call it R prime. R prime is the radius of the new data set. And R prime will be equal to R divided by alpha. Again, R was this. I drew a picture right here instead of writing out the formula, but the picture here illustrating that the radius is the farthest away distance that you are. And if we shrink all of these data points by this alpha factor, like say alpha is 10, we're shrinking everything by a factor of 10. All of these minuses, all of these pluses, all of these data points will get closer to the origin, and so our R will get smaller. And the idea here is that, okay, if we can make our R smaller, then our runtime bound over here is based on R, so maybe things will be faster. Any questions about the setup of this problem? What the problem is trying to ask? Okay. I think one of the hardest parts of these types of problems right here is just figuring out what the problem is trying to ask. That you notice that my written thing out here in bullet point 1 here is very small, succinct, not a lot of words. I added a lot of context and color here, things that you needed to just be able to understand were important for this problem. And so that's the first step. First thing that makes these problems hard is just understanding why is this a potentially interesting thing to do? Why does Alice think that this might speed up the problem, might speed up the runtime? So now to actually answer this question, we have to say, okay, if our, I'll say that our new runtime down here, our new runtime, hopefully this is orange right here, is different enough from the red that you can see it. The new runtime, I'll put primes on everything. O of R prime squared, let's write that better, R prime squared, the W star prime squared, and then the rho prime squared down here. All of these variables potentially changing by our transformation of the data set. The number of data points will stay the same though, so this n, we'll just leave it as n over here. And in order to see what the runtime of our new transformed data set is going to be, we have to calculate all of these different values. The R prime squared, we already calculated that. R prime is R over alpha right here. So we can plug that in, O of R over alpha, both of those squared. And now we need to do the rho prime squared and the W prime squared, see how those values change in order to see whether the runtime will be faster or not. So again, the intuition behind the rho variable, this is our margin. I'm going to scroll up just a little bit to this data set here so we can talk about the margin. I'll scroll back down in a second. But first let's get the intuition behind the margin over here. And recall that the margin is the distance between our points, the closest distance between our points and whatever the separating hyperplane is. So we were drawing pictures that looked something like this. This green line right here is we call that the actual perceptron. Sometimes we label it as the W star because the W star uniquely determines this line right here. And then the rho value, the rho value is that right there. The distance between whatever the closest data point is to that separating hyperplane. Intuitively, if we shrink all the data points closer to the origin, then everything's going to somehow move closer to this green line right here, and we're going to shrink the rho value as well. The question is, how much is rho going to shrink? So I've scrolled down again now so that if you were writing stuff down below, hopefully you can see it again. But again, the rho prime is the new margin. And what exactly is the definition here of the margin? Well, the margin was the smallest distance, so rho prime would be the minimum distance over all of the x's between the minimum distance I'm forgetting exactly how I defined the rho prime last time, so I will come over. Again, one of the reasons why we need these definitions is because we're going to be having a lot of variables going on. I want to make sure that I get the rho prime defined the same way that I did before. That's not where it is, sorry. The definition is located in the notes packet right up here is where I want us to go. Here we go. On problem 3, I scrolled up the notes packet like 2 pages right here. This rho prime is the thing that I wanted us to get right here. This rho variable, the margin variable, and I want to make sure I get our notation consistent here. So the minimum of yn w star x of n. So scrolling back down to the actual problem now, rho prime here is the minimum of the y sub n w star transpose x sub n. Slightly confusing thing here, these n values, and this is the minimum over the n's in our data set. These n values are lowercase in lowercase, which means they are the like indexes into the data set. Into the data set, but the textbook uses the uppercase n in uppercase for the total number of data points. In upper for total number of data points. So you just got to be careful about like when you're using the lowercase and upper, keeping track of what you're doing here. Well, here this rho prime, in order to, rho prime defined in terms of x prime. This x was an x prime right there. In order to see how this compares to the original rho value, the original x value, what I'm going to do is I'm going to substitute my my formula that Alice is suggesting for x prime up here, and we'll jump down here. So the rho prime equals the minimum over the n's of y sub n w star transpose. Now it's x sub n divided by alpha. This constant right here, this alpha, is not affected by the minimum, doesn't interact with the minimum, so we can pull that out. So we get 1 over alpha up front, minimum y sub n w star transpose x sub n. This whole thing on the right-hand side is equal to rho. That's the exact definition that we had. So rho prime is exactly equal to rho divided by alpha. Substituting in for our equation right here. This is our runtime, again, where we're going our new runtime. We substituting all these primes, calculating these primes and substituting them in. We just calculated rho prime is the original rho squared divided by alpha squared. The last thing that we have to do here is the w prime star. And the entire reason we did the big discussion yesterday about the picture and visualizing these pictures is so that we can understand this w prime star and what's going on right here. So the tempting thing, again, the tempting thing which is incorrect, we talked about why this is incorrect last time. The tempting thing which is incorrect to do is to say that, oh, this w star right here, this looks like a hyperplane. And I know from my linear algebra class and all the other classes that I've taken that every hyperplane is uniquely defined by a perpendicular vector to that hyperplane. And that is a true statement, but this perpendicular vector right here, this is not equal to w star. Not equal to w star. That's the common mistake that students make, is that looks like it should be equal to w star. This hyperplane right here is commonly labeled as w star because it's uniquely defined by w star, but it is not actually equal to w star. The reason, again, is that all of these points, there's this hidden one dimension sticking up outside of the page, hidden one dimension sticking up outside of the page, and this is the actual w star defines a hyperplane like this coming out of the page, with the perpendicular vector pointing that direction, some totally different direction than this right here. So when we do the shrinking by the factor of alpha here, we are not moving this w star closer to the origin. W star does not shrink by a factor of alpha. Instead, what's going to happen is w star rotates by a factor of alpha. The points here that are sticking out of the origin, they will come closer to the origin. They will move this way. So our w star, like this separating hyperplane immediate stars here, it will rotate like this. It will rotate like this. It will change, but the actual magnitude of it will stay the same. And that's what we did yesterday or Monday in class, that the magnitude of w star is going to be staying the same here. It's just going to be rotating. Sorry, I'm just going to plug that in here real quick. It'll take me second to finish up the thought and then get questions. So because the actual W star stays, the magnitude stays the same, the magnitude of W prime star equals the magnitude of W star, even though W prime star is not equal to W star. There's a rotation going on there, but it's just a rotation, not changing the size. So we can still say over here, W star squared, still times n. These alphas cancel out. These alphas cancel out right here, and our overall runtime stays exactly the same. The overall runtime stays the same. It should be intuitive that the runtime stays the same here if we are scaling the data. If that was something that could potentially like make the runtime better, then we would always just scale the data to be like really, really close to the origin to make the runtime instant. But this is a intuitive level proof, not a formal proof, but like capturing the intuition behind why that's not the case. That our runtime is based on the R in the row, and when we try to manipulate the R through a formula like this, it is also going to counteract the runtime boost by changing the margin value. There are other transformations that you'll see in the next parts of this problem, which can affect only the row or only the R, but this particular transformation here affects both of them equally, and it balances out. Okay, that's everything I wanted to say. The question, yes. The question is on the right side over here where I have an N. This is in fact the letter N and not the letter pi, yes. And that letter N is the, actually I guess it should be an uppercase letter N because again, the book uses an uppercase N for the total number of data points. That's the sort of notation that is not consistent between authors, and so I might accidentally make this mistake, but these should be uppercase N's because it's the total number of data points over here that things are, that affects the runtime. In general, it should be like, in some sense, obvious that it only makes sense to use the lowercase n or the uppercase n. Like only one of those things can make sense. There should never be like semantic confusion about them, but I will do my best to be consistent like this. Yes, good question. Not pi's. They are also not lowercase n's. They are uppercase n's. Scroll down a little. Okay, yeah, while people are still writing things down, one last thing that I will say is, I said this is the most important type of problem in this class. The reason this is the most important type of problem is, again, on like a capstone project or a thesis project or a real world thing you do for your company after graduating relating to data mining, is you're never going to like implement the perceptron from scratch. But you will somehow transform your data to feed it into the perceptron. And there are things that you can do to transform your data that are good, and you have things that you can do that are totally neutral and things that are bad to do. This is an example of something that is totally neutral to do, at least for the runtime. And so you wouldn't want to do it. It's just wasting time to do it. The other two problems down here are exploring similar things. I will say that for part 2 and part 3, the last two parts here, one of these improves the runtime and the other one is neutral. So it's a hint to, as you're working through the problems on your own, one of them improves the runtime, the other one is totally neutral. Up, yes. Right there. Okay, in just a minute here, we're going to switch over to the next notes packet, the new notes packet. So you can go ahead and get that ready for yourself if you don't have it out yet. Again, there's more hard copies up here if you like the hard copies. There's 2 hard copies of things, a quiz practice that contains all the definitions that, again, you have to have memorized, and the notes packet that we'll be going over. If you are the sort of person who likes the electronic notes packets, what we would be going over next is this notes2.pdf file right here. And this is what it looks like. Okay. So everything we've done so far in class, starting with PageRank and then up to the first chapter here, the new textbook, everything we've done so far has focused only on computational aspects of data mining. And for PageRank, that was the only thing that mattered. There was only computation and there was no statistics. But for the next month to, I don't know, more than a month, we'll be talking about statistical properties of machine learning algorithms in particular. And so today we'll be introducing some of those new statistical terms, and we will not do too much fancy with those terms, just introducing them today, seeing what they mean, and the coming weeks we will be doing the fancy stuff. Chapter 2 is particularly difficult. There's 5 chapters in the textbook. Chapter 2 is far and away the most difficult here. So I guess if you need mental preparation for next week will probably be the most difficult of the semester. Most new terms, most weird things, most things unrelated to things you've seen before, probably. In the textbook, the stuff that we're talking about today comes from section 1.3, 1.4, and there's a little bit of section 2.2.3 snuck in here. So those are the readings to follow along for the notes for today. But after today, we will finish with everything in chapter 1 and start chapter 2 Monday next week. Okay, let me zoom in one more time here. Okay, so problem 1 here. One of the things that we said last time, or one of the consequences of the things that we said last time, is that the PLA will not converge if the input data is not linearly separable. We didn't say that explicitly, but that's a consequence of the things that we said last time, and one of the problems that we didn't cover in the other notes packet goes over that. But now what this problem 1 here is describing is describe 2 scenarios that cause the PLA to fail to converge. Again, PLA, perceptron learning algorithm. So the first thing I'm going to do over here is I'm going to draw what the good example is, and then I'll draw those 2 bad examples. So the good example looks like the examples that we've mostly been drawing, and our axis here, again, for simplicity, sticking in 2 dimensions on our data sets. But we have the pluses on one side, and the minuses on the other side, something like this. And the data set, again, is linearly separable because we can draw a straight line through the data set. This straight line not equal to W star, but uniquely determined by W star. And so it's often labeled as W star. And this is our perfect hypothesis that separates these two classes from each other. So this is the perfect hypothesis. The perfect hypothesis is linear, so we call this linearly separable. Hopefully the light green there is legible to you all. This is a W star, and then saying perfect hypothesis, linearly separable. And I'll just underline that same term in green up here about the linear separability. So this is the good situation. This is the situation that we've been considering that so far is that the data set is somehow divided in a way that we're able to perfectly separate it. We're going to start talking about these bad situations, though. And so let's see 2 examples of these bad situations. And all of the statistical stuff about machine learning is related to the bad situations and how bad of a situation are we actually in. So the 2 possibilities here, one is that I'll call this no noise, but nonlinear data, nonlinear data. And so this could look like, we'll put the pluses in the middle like this, and the minuses around the edge like this. And now there is a possible, there is some line that I can draw through this data set, or some curve, a circle right here. This right here separates the data. This separates the pluses and the minuses, but it's not a straight line. And because it's not a straight line, it's not linear, the perceptron learning algorithm can never come up to this conclusion. Equivalently, this is not in the hypothesis class of the perceptron. So there's no noise, but it's nonlinear data. So I'm going to draw a W star now. I'm going to draw, this is the perceptron, a possible perceptron right here. W star. This W star, this perceptron, all perceptrons must have some error, must have some error. So this is one way, one bad situation. The next bad situation is our data could somehow be like basically a straight line. So I'll draw, this is similar to the leftmost plot. Somehow could be like it really is a straight line, but there's noise. And so we might have some like accidental like minuses over here and pluses over here. And so this one, there is linear data. Like somehow the data set really like should be linear. It's mostly linear, but there is noise. And in this case, again, the data set, once the noise has been added, something like this is our best possible perceptron. Something like this is our best possible perceptron. But because of the noise, we can't get perfect error, or we can't have zero error. We can't have a perfect classification. So because of noise, no way for perfect classification. We're a little bit interested in the runtimes of these three different situations, but only very, very little bit interested in. What we're really interested in is the statistical differences of these three situations. Like how can we measure whether we're in the middle situation or the right-hand situation or the left-hand situation? How can we know for sure if we're in one of those situations? And based on that knowledge, how can we change our algorithm to make it better? So this is like these three pictures are the main pictures to keep in mind over the coming weeks as we're talking about. We'll be introducing a lot of different theorems about these pictures, a lot of different definitions, and but these are the three pictures to always make sure to come back to and see how does whatever the theorem is, how does it relate to these three pictures? Are there questions? Yes.
Is convergence defined by perfect classification or convergence?
Question is, what exactly do I mean by converge right here? So this is, again, not specifically about the pictures that I drew here or about the data here. This is about a definition from, we first used this definition in the PageRank, and then the previous notes packet will also talk about this. But this is that you get to the right answer. You say that an algorithm has converged. A has converged if you eventually get to the right answer and the algorithm stops. Eventually, they stop at the right answer. There's an informal definition of convergence. There are more formal things, but they are scary and not important. The point is that you've come to the right answer. The reason why the PLA does not ever get to the right answer is because you have it's structured as an infinite loop where you are going to every time in each iteration of the loop, you pick one data point that is misclassified and run a certain iteration on it. If you are in one of these bad situations, then you are guaranteed that you will always have one data point that's misclassified. If there is no linear line that can separate the positives and the negatives, whether that's because just the shape is not linear or because there's noise, that means you will always have something misclassified, and so the PLA will never terminate because of that. Good question. Okay, what we're going to do next, the problem right below this, is define a whole bunch of stuff. And we're going to, I put this right next to these pictures above because we're going to relate all these definitions right here to these pictures above to help us give some intuition about why these definitions are important. The first of these definitions, again, too, also for the textbook here, trying to make the notes follow the textbook very, very closely so that if there is something which you don't understand from the notes and what we do in class, which is basically always going to be the case for everybody. There's a lot of things going on here, and it's all very technical, that you have a reference, know exactly where to go in the textbook to look for these things. So the in-sample error, the textbook talks about it here on page 21. The textbook defines the in-sample error as this. E sub in is the actual variable name for the in-sample error. The E up here is the mnemonic is E for error, and then in for in-sample error. There's going to be lots of different types of errors that we talk about in this class, and it will always be E sub something. In this case, this is defined to be 1 divided by capital N of the sum of I equals 1 to capital N of these square brackety things, h of x sub I not equal to y sub I. This is the in-sample error. So what's going on here? What these square brackety things mean is that if you have a square bracket of true, that'll be evaluated to 1. And if you have we do it right below, the square bracket of false, that'll be equal to 0. So this hx sub I not equals to y sub I. If we are, if they are in fact not equal to each other, then this thing evaluates to true, which the square bracket sort of just replaces with a 1 value. Recall that the h right here, the h, this is the hypothesis that we have learned somehow. The only learning algorithm that we've seen so far is the PLA, but this is the algorithm that we have learned. The h will always be contained in the hypothesis class h. So for the perceptron case in particular, the h will be the output of the PLA is what gives us h. And this capital H is that set of all linear classifiers, x into W transpose x, or actually the sign of that. And this is for the perceptron case in particular. We'll be seeing a lot of different learning algorithms coming up, and so you'll be able to plug these things in with different algorithms. But this H is the output of that learning algorithm, and it's somehow coming from a particular set. Again, always important in this class to keep in mind what sets these we call them hypotheses or functions are coming from, because we will be proving the things that we will prove statistically will all be determined about the properties of these sets. Another thing that, so this H right here, this is our prediction of what is the classification of a particular data point. This Y right here is the actual true value, so the true label. And so again, this is seeing, is our predicted label, is it the same or not the same as the true label? We sum that up for, do that for every particular data point in our data set, and then take the average. And that's what we call the error. The error has the property. The error has the property that it will always be contained in 0 to 1 inclusive. You could be 0 and you could be 1. Another thing that the textbook does is usually they just write the E sub in all by itself without any sort of function notation. Sometimes they will put parentheses right here with an H inside of it. Sometimes they will put an H right here with parentheses inside of it. If they do that, then this H right here and this H right here are the same. Those are the same. Usually they will ignore that. Sometimes they will keep it around. To stick away from light blue. That looks hard to read. Okay, in just a second, I'm going to scroll up here and look at how this E sub n compares to these data sets up here. If our data is in fact linearly separable, then we are going to correctly classify everything in our training sets. And so the E sub n right here will be equal to 0 for our perceptron hypothesis class. But our E sub n will be greater than 0 in either of these two bad situations. It'll be greater than 0 if the data is just not linear, because we will always have some pluses and minuses on the wrong side. And similarly, even if our data is linear but there's noise, we will always have some pluses and minuses on the wrong side. So E sub n greater than 0 in both of these two cases. Where to write it? We'll keep it down low here. E sub n strictly greater than 0 in the bad cases. Question?
What's the difference between the single bracket and the double bracket?
Where do you see a single? Question is here we have the double brackets and the single brackets. What's the difference in notation here? The double brackets is this indicator function that takes a true to a 1 and a false to a 0. These single square bracket over here, this is the range set notation. Let's say, I'll go back to magenta. That is equal to the set of all x, where x is 0 is less than or equal to x, less than or equal to x, less than or equal to 1. So it just means it's between 0 and 1. Yeah, very easy to get confused on notation stuff in this class because there's all sorts of notation going on. And I will do my best to be consistent with the textbook, but authors in general are not consistent about things. Every textbook, every research paper uses different notation here. And so the things that I have in my head might be different than the textbook sometimes. A good question. Okay, so this is the in-sample error. In the in-sample error, this is something that we can directly calculate. But it turns out that the in-sample error is not the thing that we are most interested in. The thing that we are most interested in is what's called the out-of-sample error, E sub out. And there's a couple of different intuitions about the out-of-sample error. But the most important intuition about the out-of-sample error is that this is going to be our error on future data sets, future data points that we haven't seen yet. So I'll write that out in English. Error on future data. The in-sample error is something that we can actually calculate because we actually have the data that's related to the in-sample error. The out-of-sample error is something that we cannot calculate because it's about data in the future, which we don't have access to yet. And so we're going to be doing a lot of statistical reasoning to think about this out-of-sample error and make some arguments about why our out-of-sample error is going to be good or bad. Another sort of intuition about this out-of-sample error is you can think about it as like, what if I had an infinite amount of data? Then that is the out-of-sample error. So you can think of the out-of-sample error as the limit as n goes to infinity of the in-sample error. Two sort of equivalent intuitions behind the out-of-sample error. Formally, what this is this is the probability. So the textbook uses this funny-looking P, the blackboard bold P like this, to say probability. So this is the probability that h of x is not equal to y. We can see this is like an estimate of that probability up here that for our particular data, we calculated on all those data points. But what we're really interested in is the actual probability of that our hypothesis is not equal to the true hypothesis. And so the out of sample here error is defined this way. These two English sort of statements, I guess this one's in English, this one's sort of mathy. These are intended to be intuitions. They are not definitions. This thing right here, the bottom thing, is the definition of the out of sample here. Scrolling up to our pictures up above again. How does the out of sample error relate to all three of these pictures? In this case, the out of sample error, let's see, I ran myself out of room to write stuff. The out of sample error, yeah, I'll come back up here to talk about the out of sample error after talking about just the last two definitions that we need. They're both quicker. The first is the generalization error. Generalization error. This definition has no fancy symbols associated with it. You'll just see the textbook talking about the generalization error in words, and that is equal to the difference between the in-sample error and the out-of-sample error, like this. Again, the in-sample error is the thing that we know. The out-of-sample error is the thing that we want. And so we're going to try to make this generalization error be small. Some other resources, like if you're looking for other resources on YouTube or on blogs on the internet or something, some other places will call E out the generalization error. This is sometimes called generalization error. So you have to be careful here about, like, if you see somebody talking about the generalization error, are they talking about E out, or are they talking about the difference between E in and E out? Be very careful about that if you're looking at different resources. And then last definition here, I'll write it out, and then we'll talk about all three of these things in the pictures up above. The last definition is the true error, also called the Bayes error. And this is the E out of our f function. So recall from before that the f function, this is like the function that actually generated the data. Again, that was called the true function, the Bayes function. Some people call it the God function, the universe function. This is the thing that, like, the universe actually uses to generate our data. So this is the best possible function. And so the true error, Bayes error, is the best possible, is the out of sample error of the best possible function. The true error, again, does not have a special symbol formula for it, though you'll just see the textbook use the words true error or Bayes error. Okay, coming back up to the pictures now, integrating all three of those definitions together in these pictures. In the picture up above here, the Bayes error of a truly linearly separable data set, the Bayes error E out of f is also going to be equal to 0, because if we have some particular hypothesis, some particular function that's able to separate the data, well, that means the best possible function is definitely going to separate the data right here. And so the Bayes error 0 in this case. In the middle case, this type of bad situation, the no noise, nonlinear data situation, in this case, we also have that the E out of f, or the Bayes error, or the true error of our problem, is equal to 0. The difference between this bad case right here and this good case, well, the thing that's the same is that the Bayes error is equal to 0. The thing that's not the same is that the in-sample error is going to be greater than 0. the error of our particular hypothesis is going to be greater than 0. In this last bad situation over here, the third situation on the right, we have that in this case, not only is the error of our hypothesis, the E in, going to be greater than 0, it is also the case that the E out of F will be greater than 0. I got the colors blurring together right there. So this is, again, the three sort of situations that we're going to be analyzing. The first one is the best possible situation where our Bayes error is equal to 0 and the in-sample error of our algorithms is equal to 0. Everything that we talked about so far falls into this first good case. When we're only talking about computation, not talking about statistics, we must be talking about this first case right here. The reason that we start talking about statistics is because we care about these last two bad cases. Essentially, all real-world data is either nonlinear or has noise, or most likely is both of those situations. And so we care about statistics to handle these situations. The first of these bad situations, the simplest of these bad situations, is when our in-sample error of our model is greater than 0 because the data is not linear. But there is some other model that might work, and so the Bayes error is 0. And on the right-hand side over here, this is the worst possible situation where we have noise, but also the everything is going to have noise in its situation, so we have to care about this. This is where both our in-sample errors are going to be greater than 0, and our Bayes error is also going to be greater than 0. We're really the only reason we care about these first two situations, this good situation and the first bad situation, is as preparation for this third situation. All real-world situations, everything that you might encounter in practice, are this third situation. Okay, said a lot of stuff there. I haven't stopped for questions in a while. Anybody have questions about anything that's going on? Yes.
Just to clarify, you're using different models to calculate in error and out error for the second, for the first bad situation.
Yeah, it's a great question. So the question is, am I using different models when I'm talking about what's in black and what's in magenta here? Am I using different models to talk about the in-sample error and the true error right here? The true error, a special type of out-of-sample error. And the answer is yes. Anytime you're talking about the true error or the best possible error or the Bayes error, you're thinking about the best possible model that could conceivably be created that maybe nobody's even thought of it yet, but the best possible thing that could be created in the future. When I was talking about the black stuff up here, I'm specifically talking only about the perceptron learning algorithm, which is this linear model. I mentioned before that the textbook often drops the explicit dependence on the hypothesis right here, but we could add that in right here for all of this black stuff and say that H is from PLA. And one of the maybe harder aspects of getting familiar with this notation is that if we kept track of all these little subscript thingies, all of these things in parentheses as well in this textbook, if you kept track of it all the time, then we would have formulas where one variable has 10 subscripts on it. So a lot of this is just hidden from notation, so that just to make the notation more compact, and you have to just understand that it's dependent on those things. But yeah, so there's a great question. All the stuff that I wrote in black here, everything that I talked about with the in-sample error was specific to the perceptron learning algorithm, specific to the linear model case. But the stuff in magenta, the stuff about the true error, is about the best possible model that could possibly be created by whatever super intelligence is in existence 1,000 years from now, using all compute and if whatever your deity of choice is came down to Earth and used all their powers to create a machine learning model. That is what this magenta thing is. Intuitions behind all these things, getting actually comfortable with them just takes a lot of work. Again, memorize all these definitions is something that you will have to do. I will be going through these definitions in the future very fast, just assuming that you have an obvious intuitive understanding of these things. And so you really need to sit down and start memorizing them. You may have also in previous courses seen some of these terms in a more intuitive sense, or seen them in a more intuitive sense on like different blog posts and things. If you feel like you already understand these terms, do not get led into a false sense of confidence about that, because we're going to be getting very technical very quickly here in all of these definitions, and you will need to be able to like instantly come back to these technical definitions here and do stuff with the technical definitions. It is not enough to have an intuitive understanding. That's very important as well, but you also need to be able to go straight to these technical definitions and work with them, manipulate these technical definitions. Okay, there's a lot of explanation on the very first page of the notes packet. So hold your horses. We're going to get even more exciting and technical here on this next part right here. So this first note up here is just explaining that the thing that we really care about, the like entire discipline of machine learning, can in some sense be summarized as trying to understand the out of sample error. That's what we always do, is we try to understand the out of sample error. That's like what my research is about, what all the people who work at OpenAI, all they think about is understanding the out of sample error about their algorithms. And there's a lot of tools for doing that. We're going to be covering many of them in this class later on. But the first one of those tools, the most important of those tools, is this Hoeffding inequality. It's a German name right here. Can be hard to pronounce these different terms, some of them that we'll be seeing. But Hoeffding is how we pronounce it. And in the textbook, there is an informal presentation of the Hoeffding inequality, which is a little bit, I think, unfortunate, because they do rely on it in many situations. And their informal definition makes it a little bit harder to like exactly appeal to it. And so I have restated it right here in a maybe a more compact form that's easier to reference. Less easy to understand for the first time, but easier to reference it after you have understood it. Again, the reference in the textbook, equation 1.4, this theorem as stated, not in the textbook. As stated, not in book. Just the intuitions in the book. So there's a complicated thing. We need to wrap our head around what's going on here with this inequality that's going on with this theorem. And we're going to draw a picture in order to do that. I'm going to explain all the different terms and variables in this definition as I draw the picture here. First thing I'm going to do is draw some axes for our picture, like this. Draw some axes for our picture. And this probability, this again is a probability distribution. This P right here is the probability, the textbook's notation for probability. We want the probability that this nu minus mu variable is at least epsilon. And so what are this nu and mu variable? Again, this like V looking thing right here, V looking thing that's pronounced nu. Pronounced nu. People will look at you weird if you call it V. If you call it anything other than nu, people will look at you weird. I will look at you weird on your exam if you're talking to me and call that V. I won't know what you're talking about. This thing looking here right next to nu looks like it's called mu. So mu and nu, these are the two variables that we have of interest right here. Mu is commonly used for like the center of a probability distribution, like the mean of the probability distribution. So mu is the mean. Anytime you see people talking about mu's, they're probably somehow talking about like the mean or the average of the probability distribution. And this theorem here has this nu because it's the letter right next to it in the Greek alphabet. So it's common to see those two letters used together. Where this new variable is coming from is that if we have some sort of data set, so I've written this out very generically right here, where these A values do not necessarily have to be the same sort of X's and Y's that we've been talking about, just any collection of numbers right here. And this collection of numbers satisfies that they are between 0 and 1. Then when you add them all together, taking the average, so this is what the definition of new is. New is like the empirical average. And when you add all those things together, the empirical average will be very close to mu, the true average. So mu here defined to be the expectation of nu. I'll draw all that out now so that that makes maybe a little bit more sense. Okay, so we'll have some sort of probability distribution-ish thing looking like this. We'll have like the center of that. This is the mu value. Again, like the true mean of our probability distribution. The then this let's see, the x-axis here is like our new variable, where we are on our x-axis here. Like if we sample from a bunch of these A values, we get a bunch of these A values, how close are we going to be to the mu value? This is a probability distribution of how close our empirical sample is to the true sample. So this point right here, this point right here is the probability specifically of nu at that point in this graph, the shape of this graph. This is the probability of what our empirical sample is. The textbook will very often summarize this probability with the Greek letter delta. And so the y in this graph here, I'm going to label as a delta value. We'll be seeing a lot of deltas throughout this class. That's going to be this probability. Anytime you see a delta, think probability. And then anytime you see an epsilon, that's going to somehow be an error term. In this particular graph, the epsilon value is the difference between, you think about it as the difference between our true error or our true mean value, our mu right here, and our nu value. So this like distance right here, and let's see, I'm going to stick away from the cyan. Let's go to gray. That distance right here is the like the epsilon value, that it's this difference between our two our true error and our sample error. The whole formula over here is what this formula is saying is that the shape of this actual distribution is essentially Gaussian. The shape of this distribution is basically Gaussian. I'm going to put basically in quotation marks. We don't need to know like exactly how it's different than Gaussian. You can think of it as being Gaussian. That gets you all the intuition that you need. Shape is basically Gaussian. Again, Gaussian distribution being the same as a normal distribution. Technically, because there is a less than sign right here, this is sometimes also called a sub-Gaussian distribution. You'll see all those terms used sort of interchangeably in the textbook. Actually, the textbook will use all those terms exactly interchangeably. But you can always think anytime you see any of those terms, it's just Gaussian, and that will get you the intuition you need. The important thing about this right-hand term, besides that it's Gaussian, let's scroll down a little bit so you can still see that, is this in factor over here. And so this size of E, this distance between our true sample and the true value of this distribution and what we actually observe, this is, it's that size is somehow like 1 over n squared. The squared coming from the epsilon over there, and the n coming, sorry, not 1 over n squared, 1 over the square root of n. The square root coming from the squared factor right here, and the n, yeah, The important thing here is that the n's on the denominator. So if we add more in right here, add more data, if the number of samples, these number of A values we have, if that gets bigger, then this epsilon is going to get smaller, and our new value will get closer to our M value. This particular theorem right here is, so it's called the Hoeffding inequality. It is an example of a central limit theorem, example of, and in particular, a finite sample, sometimes see CLT for central limit theorem. CLT equals the central limit theorem. And basically, like if you're in a statistics course, in some sense, the whole point of a statistics course is to prove some version of a central limit theorem. We're not going to prove this theorem in this course. We're just going to use this as a tool to talk about different machine learning algorithms and why you might want to choose one in one situation and one in another situation. Yeah. Said a lot of things. Any questions about anything that I said? Yes, Angelina. The question is, where is this delta sign? What am I trying to mean by this? I'm saying that I just renamed this probability as delta. Delta, say by definition, I said delta equals this probability, and so this vertical axis I'm calling delta. I could have equivalently called this vertical axis the probability of all that stuff inside of it. I just didn't want to write out that whole equation. And in general, in the textbook, you will see a lot of deltas. Delta always refers to a probability, and epsilon always refers to like a non-probability thing, an error, like how close is something to whatever the true something should be. I don't know if that answered your question or not. Yeah, the question is, so what exactly are mu and nu? I think the way to answer this, the way to actually get some intuition with this theorem is to start applying it into some situations, and that will help clarify some things. The point of this problem right here is just to see that this is a Gaussian-ish thing, and yeah, that's the important thing about this problem. It's Gaussian-ish. Okay, if things are not clear yet, there's problems to make them clear. We're not going to have enough time to fully walk through the steps of this problem 4 right here today, but we will have enough time to talk about the stuff that you need to do in order to be able to do it on your own. And I'll highlight that for all of the parts of problem 4 right here, I have provided some like the actual answers right here in the notes packet, so you can go through this, try your work, plug things into the theorem, see if you just know how to mechanically use the theorem on some different values, and you know you are in a good place understanding things if you're getting the right answers down here. There's 4 different parts to this. They all have the answers provided like that. So the question is like, we have this theorem. Why did we bother introducing it? There's a whole bunch of letters and scary notation going on. How do we apply it to the things that we care about in machine learning? This problem 4 is going to introduce a new thing called the training set. So a lot of just like new definitions going on today, the training set. And the training set is this additional data set that we are creating to help give us, sorry, we already have the training set. It's the test set that we're introducing. The training set is the thing that we've been talking about with the perceptron learning algorithm, the data that is the input to the algorithm. Training set is the data that is the input to the algorithm, data, input to the algorithm. The test set over here is our way of estimating E sub out. Our way of estimating the true error, E sub out. Again, we can't compute E sub out directly because E sub out, one intuition is that if you have an infinite amount of data, another intuition is that it is about the data that you have not seen yet. And so we can't actually calculate this directly. The only thing that we can do is provide some sort of statistical guarantee about E sub out. And the test set is going to do that for us. In these problems down here, this E sub test right here, this is going to be your new value. You set E sub test equal to the new variable. Again, this V looking thing is a new, and E sub out equal to mu. And if you do that, then you will satisfy all of the conditions for the Hoeffding inequality. It is important for you to check that this thing over here does in fact satisfy the conditions of the new variable and the mu variable. So it's important for you to check your understanding there, taking this, applying it to that theorem up above. And if you do that, then recognize this one fact right here. Plugging in the numbers will get you this answer right here. So if you're able to solve this this problem right here, get this number, then you will have then you have the good understanding. You have the understanding of how to match the test set to the to this theorem definition up here. We're almost out of time, so there's just one last thing that I want to say about this. If you have taken a statistics class, so again, statistics is not a prerequisite, but if you have taken a statistics class, this epsilon that we're using, this is like a confidence interval. Confidence interval, that's another intuition. So this whole problem is about calculating confidence intervals. This epsilon right here, you can think of it again like this confidence interval. How confident are we that the thing that we are using that is a summation, an average of a bunch of things, how confident are we that that is close to what the true average should be? And so these problems down here are about calculating confidence intervals, calculate the difference between E test and E out. How good is our test set compared to the true error? How good, like this finite sample of test data points that we have, how well does the error on that finite set of samples, how well does that represent the error that we're going to get on all future samples if we take all infinite amount of data in the future? So I started talking about all this because the original question was like basically, why do we care about this theorem? So this problem right here is the simple explanation about why we care about that theorem, just being able to calculate these confidence intervals. The next two problems down here are things that you should also be able to do at this point. And I'll say that the next two problems are things that are more important for future exams and real life, that the stuff below here, these problems, stuff below here, most important. So yeah, take a look at that for the weekend for class on Monday. We're a little bit behind right now from where I was hoping to be at this point in the class. We slowed down a little bit this week for the midterm exams. But Monday we will come back here. We might talk a little bit more about this, come with questions on Monday or office hours Friday, but we might just jump into the next note packet too. I'm not sure. That's it for today. If you have questions about anything at all, homework, coding, this notes packet, happy to stick around and answer them. Otherwise, have a good weekend and good luck studying.
My bad.